This is Physical Chemistry, Part 2, Chemical Kinetics, Chapter 33, Kinetic Theory of Gases, Section 33.1, Kinetic Theory of Gas Motion and Pressure. So first, let's compare the size of the gas particles with the volume of the container of the gas. We'll use argon as an example. The diameter of an argon atom is roughly 0.3 nanometers or 3 angstroms. Its radius is 0.15 nanometers. Its volume, using this equation, is 0.014 cubic nanometers. So now let's compare the size of 1 mole, or 6 times 10 to the power of 23 atoms, with the total volume of the container. We can do this calculation. Over here, this is the volume of 1 argon atom times this Avogadro constant. This is the size of 6 times 10 to the power of 23 atoms. The denominator is the volume of the container for this 1 mole argon gas. I used PV equals nRT here. N times R times T over pressure in Pascal. So all numbers are in SI units over here. This is not SI unit, but 1 nanometer is simply 10 to the power of negative 9 meters. So 1 cubic nanometer is 10 to the power of negative 27 cubic meters. Do the calculation, you'll see the argon actually occupy a very small portion of the total volume of the container. In this case, less than 0.1%. So typically, gas particles occupy around 0.1% of the total volume of the container. Well, the rest of the space is empty space. You may watch this YouTube video to see the motion of argon atoms at 300 Kelvin. So argon atoms actually move at several hundred meters per second. So in this video, the motion of the argon atoms is slowed down significantly. In this video, you'll see collisions take place between the argon atoms. But overall, these atoms travel as a separate and unperturbed entity until it collides with another article or with a wall of the container, and then it changes the direction. Now let's look at the equation for velocity in a 3-dimensional space. So this V with an arrow on top is the velocity. It can be decomposed into the velocity in the x direction, y direction, and z direction. Illustrated in this picture. This V vector is a 3-dimensional vector. Its projection on the z-axis is V sub z. Its projection on the x-axis is V sub x. And over here, this is the projection of this V vector in the y-axis. So we can tell V squared is equal to Vx squared plus Vy squared plus Vz squared. So from here to here, we just need to multiply both sides by 1/2 m. M is the mass of the particle. So 1/2 mv squared is the translational energy. 1/2 mvx squared is, well, the translational energy in the x direction. This is the translational energy in the y direction, in the z direction. We now derive the ideal gas law, PV equals nRT, for ideal gases. We'll have to assume all collisions are elastic. In an elastic collision, the momentum and kinetic energy of the colliding particles are conserved. So you may watch this YouTube video to see an example of nearly elastic collision. Okay, now let's derive. Assuming we have n moles of argon atoms in a box, but let's look at just one atom at a time. And let's look at the motion of this single atom in x direction. Assume the speed of this atom is v sub x in the x direction. It's moving towards the right direction. It's about to collide with this shaded area. So let's just imagine it's going to move that way, collide with A, bounces back. So look, the velocity changes sign, but again, the speed remains constant. So it's going to move towards left after collision at the same speed. Collides with A2, bounces back, and then collides with A1, and then A2, and then A1. So pay attention here. After this particle travels how much distance before it gets back to the original position? Well, let's say this dimension is L. Then this particle will have to travel a distance of 2L before it gets back to the original position. So that's 2L. Another collision here, and a collision here, and get back to the original position, 2L. This is very important. Now, let me just tell you the average kinetic energy of each gas particle in each dimension is half kBt. So this can be proven in statistical thermodynamics. So we'll deal with this later. For now, let's just accept this fact. The average kinetic energy in the x direction is half kBt, and so is the y direction and z direction. By looking at these equations, you can tell the total translational energy of a gas particle is 3/2 kBt, considering all three dimensions. Now let's study the collisions between this atom and this shaded area. So one question here is, how many collisions may occur between a typical argon atom and the shaded wall within a time interval delta t? Within a time interval delta t, this argon atom can travel a distance of Vx delta t. So I'm assuming this Vx is a constant. The speed of this argon atom never changes. And therefore, we can simply use this Vx times delta t. That's the total distance the argon atom travels, divided by 2L to get the number of collisions within this time interval. Again, every 2L distance, this atom collides with this shaded area once, right? So every 2L. So one collision, bounce back, and then get back to the original position. So after this gas particle completes this travel of 2L distance, it gets back to the original position. And then the next cycle, it travels another 2L distance and finish another collision with this shaded area, this A1 shaded area. So again, every 2L distance, there's one collision. The total distance is Vx times delta t. Therefore, this equation tells us the number of collisions within time interval delta t. Now let's look at the momentum change caused by the collisions within delta t. Look, each time when a collision happens, the velocity of this gas particle changes from Vx to negative Vx in the x direction. So the change is negative 2m times Vx in momentum. However, for simplicity, let's just look at the magnitude. So the magnitude is 2m Vx as the change of the momentum of the atom in a collision. All right, so the momentum change within time period delta t is the number of collisions within this time period. So it's Vx times delta t over 2L. That's the number of collisions. And over here, this is the amount of momentum change. So if you multiply these two together, we'll get the total momentum change caused by the collisions to this traveling argon atom. Now, what if we have n mole argon atoms? So n mole atoms is n times this Avogadro constant, so n times n sub a atoms. And then we'll have to sum up all the changes in momentum for all these n mole atoms. So in total, the momentum change caused by the collisions to these n mole atoms is this. We'll have to use a sum sign here. So it's going to be just the sum of the momentum change of individual atoms. We'll have to put a dummy variable I here. This is the label. So we sum over from the first atom, second atom, all the way to the last one. The last one is labeled with n times n sub a, assuming we have this many atoms. So again, this is just the sum of the momentum changes of all atoms. And then you can see this delta t, this L, does not depend on I. So I took it out here. And then we have delta t over L times the sum of mvx squared. Again, this I is a dummy variable. I is from 1 to n times the Avogadro constant. So in this term, we have this many atoms. Now let's further simplify the sum. Remember, the sum of multiple data points is simply the average times the number of data points. So we have the number of data points here, and we have the average here, right? Together, the product of the number of data points times the average of the data points is the sum, all right? And then we can convert this to kBt. So this was given to you. Remember, the average kinetic energy in the x direction is half kBt. Therefore, the average of mvx squared is 1 kBt. Now we can further simplify this because kb, the Boltzmann constant, is simply R, the gas constant, divided by the Avogadro constant. Therefore, the product of this n sub a and kb is the gas constant R. So we combine this, we get nRT. And we have this delta T on top, L on the bottom. Now let's review Newton's second law. It states that if the momentum of a particle changes, it's caused by an external force. And the equation is F times delta T is equal to delta P. Now we have this delta P here. Can we calculate the force? Yes, it's delta P over delta T. So we use this equation from Newton's law, and we plug in the expression of delta P. It's right here. And then we have this momentum change of all argon atoms within time period delta T divided by that time period. All right, we have the expression for the force exerted on that shaded area. It's nRT over L. It does depend on the width or the length of the box. Okay, finally, let's look at the pressure. Pressure is force over area. So it's nRT over L over A. And look, L times A is simply the volume of the container. So therefore, we have pressure is equal to nRT over V, and we have PV equals nRT. So I want to show you this L and A again of the box. So this is the surface area A. All right? And from here to here, this is L. So L times this shaded area A is the volume of the container. So again, we just proved PV equals nRT using the collision theory. In this derivation, we also assumed that there's no attraction or repulsion between the gas particles, because if there is attraction, the gas particles will pull each other towards the center of the container. That will reduce the momentum change and reduce the pressure. Well, if the gas particles repel each other, that will increase the momentum of those particles towards the surface. All right? And then that will increase the momentum change undergone by a particle in a collision. That will increase the pressure. So again, attraction reduces the pressure. Repulsion increases the pressure. Also, we assumed the size of the gas particles is 0. If the gas particles have a finite size, that will slightly reduce the distance traveled by a gas particle between its consecutive collisions. It does not have to travel the full 2L distance to complete another collision. So in this case, that will increase the number of collisions per time period. And also, it's going to increase the pressure of the gas consequently.